Welcome to the first video in a series of 6 about solving systems of linear equations in 3 variables. This video provides general information. But what is a linear equation? Well, it's an equation with linear terms. What is a linear term? It's a number or a number times a variable. For example, this is a linear equation because every term in it is linear, meaning either a constant, like the number 13, or a number times a variable. Linear equations are characterized by not having exponents, not having variables in denominators, not having radicals, or absolute values, or any other functions like logarithms or trigonometric functions. That's essentially what a linear equation is. What does it mean for something to be a solution to a linear equation? Well, for example, it turns out that x equals 5, y equals 4, and z equals 1 is a solution to this equation. And in a minute, I'll show you what I mean by that. But it should be pointed out here that video 1 in this series, the video you're watching, is not a how-to video. It just shows you some ideas of what it means to be a solution and what different solution types we can encounter. So where did I get 5, 4, and 1? Guess and check. And watch how it works. If I take the variables in my equation and I replace them with 5, 4, and 1 in that order, it turns out I'm going to get what we call a true statement. Let me show you what I mean by true statement. If you do the math on this, 3 times 5 is 15, 2 times 1 is 2, you get a statement that's true. Now this is an equation, but I'm calling it a statement because it is. It's the statement that 15 minus 4 plus 2 does equal 13. I'll pause while you work that out and confirm that in your head. You should have just confirmed that this is in fact a true statement. Because it's a true statement, we call x equals 5, y equals 4, and z equals 1 a solution to this equation. You'll also hear the phrase that the numbers satisfy the equation. Satisfy in math just means true. We often write our solutions with parentheses around them and commas to separate the variable values. We would call this an order triple because it's 3 numbers and they're in order x, y, z. So let's take a look at the solutions for this equation. We've just showed that 5, 4, 1 is a solution to this equation. Before we go on, I should note, this is not what you'll be doing in a mathematics course. Nobody will ever ask you to find 3 random numbers that happen to work or satisfy an equation. I'm doing this to show you what it means to be a solution. Now it turns out 5, 4, 1 is not the only solution to this equation. I used my guess and check skills and I found out that 780 is also a solution to this equation. Watch and you'll see. Taking the variables, replacing them with 780, doing the math, you can confirm by looking at this that in fact is a true statement. I'll pause while you confirm it. Again, if you're wondering where I got 780, just guess and check, and this isn't something that you would actually do in a math class. But what I've shown here is that there are 2 ordered triples that satisfy this equation, or that are solutions to this equation. Well, just to make a point, I found many more solutions to this equation. And if you're wondering where I got all these, I was not about to do guess and check, so I wrote a computer program to find them. But even though I've shown more than a dozen solutions on the screen, it should be noted that there is a never-ending list or an infinite list of ordered triples that satisfy any given linear equation in 3 variables. By the way, I made the last one a fraction. You'll notice, just to make the point that solutions are not always whole numbers. The takeaway from this is that any single linear equation with three variables, typically x, y, and z, will have infinitely many solutions or infinitely many ordered triples that satisfy that equation. So what is a system of linear equations? Now that we've seen one linear equation, a system is just more than one. And what we're going to be focusing on in this 5-video series is systems that have three equations and three variables. We typically call those variables x, y, and z. We could call them any letters we wanted, but x, y, and z are the typical ones in math courses. Now, I used some more of my guess and check skills to find out that 4, 4, 4 is a solution to the top equation here. You can see it yourself because 4 plus 4 plus 4 equals 12 is a true statement. Now, it turns out, though, that 4, 4, 4 is not a solution to the second equation, nor is it to the third, which brings me to my point of what it is we're looking for in a system of three equations and three variables. We're looking for a single ordered pair ordered triple, that satisfies all three equations. And so while I found an ordered triple that satisfies the first one, it doesn't satisfy the second or third one, and therefore 4, 4, 4, while it is a solution to the top equation, is not considered a solution to the system as a whole. Now, by my guess and check skills, I found, by randomly plugging numbers, that 462 is also a solution to the first one, and it turns out to be a solution to the third one as well. If you're not sure what I mean by that, pause the video and confirm for yourself that 462 is a solution to the top and bottom equations. But it turns out that it's not a solution to the second equation. So I say again, we're looking for an ordered triple. That's one single ordered triple that satisfies all three of these equations. That is the goal on a system of equations. Now, I used my algebra skills, the kind that I'll be showing you in video 2. Using my video 2 algebra skills, I found out that 6, 7, negative 1 is a solution to all three of these equations. And therefore, we consider 6, 7, negative 1 a solution to the entire system. Remember, this is not a how-to video. I haven't showed you how I got that. I'm simply pointing out that I found an ordered triple that satisfies all three equations here. It turns out that that's the only ordered triple that satisfies all three of them, and therefore we can call this a system of linear equations with one solution, that solution being 6, 7, negative 1. Again, in video 2 and beyond, I'll show you how to find these numbers. But systems of linear equations sometimes have no solution. It's another possibility. And there's one other, and I'll show you one of those in a minute. There's one other possibility. Systems of equations can have infinitely many solutions. I don't mean that the individual equation, I'm not talking about the individual equation here. Any one of these equations has infinitely many solutions. We saw that on the previous example, but there are entire systems that have infinitely many solutions. Let's look at the no solution variety first. Here's a system of equations. And one thing I discovered about it is that 5, negative 1, negative 1 is a solution to the first equation. That number, that ordered triple I should say, also happens to satisfy the second equation. But it does not satisfy the third equation. Therefore, it is, of course, not a solution to the system as a whole. But this system has a unique property, and you wouldn't know why necessarily at this point. unless you know a lot about systems of equations. But it turns out, for this particular system of equations, any ordered triple that you can find that work for the first two is guaranteed 100% not to work for the third. Not just the example I showed, but any ordered triple you find that works for the first two won't work for the third. And nothing special about the first two. For example, if you found an ordered triple that satisfied the first and third equation, it's guaranteed not to satisfy the second one. There simply doesn't exist a solution or a single ordered triple that satisfies all three of these. Now, how would you know that? Well, we'll discover that in video 2 and beyond. But for now, I'm simply saying that this particular system of equations has no solution at all. And that's a possibility when you have a system of three linear equations in three variables. Side note, in some courses, they use this symbol to represent no solution. That is not a zero. I repeat, that is not a zero. That is a circle with a slash through it, and it represents, in these contexts, no solution, but in general it's called the empty set. You may see that symbol instead of the phrase no solution. Either which way, this system has no solution, and we'll see in video 2 and beyond why that's the case. This system on the bottom here, it turns out, has infinitely many solutions. How do I know? I use my video 2 skills, and we're not there yet, but let me point out some facts about it. I found an ordered triple, and it turns out this ordered triple satisfies each equation in this system. Well, how is this different from the problem at the top then? Because of the problem at the top, the system at the top, I found 6, 7, -1, and I discovered that that ordered triple satisfies all three of those equations. So what makes the bottom one different? Well, it turns out, unlike the top one, where that's the only ordered triple that satisfies all three, the bottom one has other ordered triples that satisfy all three. For example, -2 to -2. If you were to pause this video, and I'm not recommending you do this, but if you were to pause this video right now and plug -2 to -2 in for x, y, and z, you would find out that all three of these equations are satisfied. And I wrote a computer program to find even more ordered triples. Any single one of these would satisfy all three of these equations. And again, this is not an exhaustive list. There's an infinite list of ordered triples that would satisfy all three. How do I know? Video 2 skills. But for now, suffice it to say that there are infinitely many solutions to this system of equations. And while I haven't showed you how to solve a system of linear equations in three variables, it's worth starting this video series by saying, in any system of linear equations, there are only three possibilities, and you see them all here in green. That the system has one solution, or that it has no solution, or that it has infinitely many solutions. Now, before proceeding to video 2, I have to give you a warning about it. To be successful at video 2, you have to know from previous algebra courses how to solve a two-variable system with two equations, because what you'll see in video 2 is you'll see a system of equations in two variables like this one. You'll see a call-out bubble appear and an answer with no algebra shown in between. Why is this? Well, because in video 2 we're solving systems of equations that have x, y, and z, and it gets very messy. And if I were to show the algebra for the two-variable systems that arise while solving three-variable systems, it would get so algebraically messy you'd lose track of the bigger picture. So what you're going to see in video 2 is a system of equations with two variables, typically x and y, or maybe x and z, a system with two variables will appear. The answer will appear as if I waved a magic wand, because the algebra is not shown. Again, video 2 presumes that you can do these kinds of problems. So either pause this video now and convince yourself that you can find that the solution to this system is 5, 7. And by the way, I don't mean plug in 5, 7 and see that it works. That's easy to do. Could you have found 5, 7 if I didn't tell you it was 5, 7? And if you can't, then please go back and watch my video called Systems of Linear Equations in Two Variables, because you will not be successful at the 3 equations and 3 variable problems that we're going to see in video 2 and beyond until you've mastered that skill. And that completes the first of our 6 videos in this series.